window. There are four things you need to understand about me to understand this talk. The first is that I'm mostly a software architect. I work with organizations that deal with very, very large software intensive systems at scale. Second, I do a lot of my research on the cusp of neuroscience and software engineering, really in the realm of artificial general intelligence. That's the work I do in embodied cognition. And then next to last, I'm the IBM client representative for NASA, so I'm deeply involved in all the things we're doing in space. Lastly, I got my first email address in 1979, so I've been doing this thing for a little while. Think of the next several slides as an example of demand pull for where I see the future going. Indeed, I'm going to begin with cellular communication, but not the kind of cells you normally might think of. I'm talking about organic cells. If you study the biochemistry of cells, you realize that a lot of the work that's going on in this space deals with trying to understand the mechanisms of communication among the various parts of a cell. Indeed, if we look at development evolution, you'll find that at some level of abstraction, every complex system, from a cell to any of the things we're working on the web, it's a message passing system. And the neuroscientists, the biochemists, I think are working from that framework as they try to understand the mechanisms of cells. From an evolutionary point of view, there was a problem that biological entities faced, and that is that as organisms became more and more complex, then the speed of transmission of information via cellular means or chemical means was a little bit too slow, and thus evolved about 1 billion years ago, give or take a few 100 million years ago, the notion of a neuron, which was the first biological instance of a communication mechanism that transmitted, rather than chemicals, that transmitted via electrical signals. Now, of course, from this collection of neurons, it brought us to us. And so let's quickly jump forward to the 1800s, where we began to see some really interesting communication networks come into play. This is actually a picture from the Civil War of the Union Army's balloon corps. Yes, there was a balloon corps. And these were the earliest things used for surveillance of the Confederate troops. How did communication work in this place? Well, a man would go up in a balloon, he'd drift over an enemy battleground, he'd land back down. So it was all voice kind of communication, not especially effective. You could be shot down, and they sometimes were, but it did work. There's a delightful book that talks about this and its connection to the telegraph at the time, Mr. Lincoln's T-mails, and you'll see the beginning of, let's call it, physical and electronic networking is described here. Another book that's quite interesting is the one by Tom Standage on the Victorian Internet. Jump forward a few decades and we're now at the realm of the Sputnik, which of course transformed, at least in the United States, the research agenda that we had. Because all of a sudden we had this small device orbiting around us, sending out a beeping signal, downlinking to us on an analog signal, on an analog channel, making its presence known. And the Cold War was really born from this point. As we, the US, put more and more things into the air to look over the bad guys, and there's a whole history here associated with the SAGE, the semi-automatic ground environment, and all sorts of interesting communication things happening there. We realized that we wanted to take images, but there was no real infrastructure to allow us to get that data back to Earth other than by literally taking pictures on film and dropping them by parachute to be picked up. So this is, a really interesting way of getting your data to you. Nothing beats, as somebody has said, a truck full of hard drives hurtling down the highway. That's, pretty great way to pretty high bandwidth. But as we moved more and more things into space, then clearly this became a problem we needed to solve. As the Cold War continued and it fueled our space race, then we saw programs such as Project Mercury come into play. And there was a tremendous amount of engineering that had to take place to deal with these now human-manned things, human serviced things that were going around in orbit, and we had to keep track of where they were and deal with telemetry and all that. So the NASA and the military began to develop an infrastructure of radar and telemetry sites that could cover this as it passed around. As we moved from Mercury to Gemini to Apollo, there was quite a rich infrastructure that came into place in space. On the lunar surface, there was a variety of voice and data communication and a number of X-band and S-band communication paths to send information from the surface of the moon back to Earth. But remember, we're here in a phase of computerization that was still in the very earliest phases. And so you had this combination of analog as well as digital communication. As we started pushing satellites further and further out, and as we started exploring deep space, Eberhard Richthofen, one of my heroes, developed NASA's Deep Space Network, which was a series of three radar installations that would ensure that as the Earth turned, we could always be in touch with something in deep space. In fact, if you look at the Deep Space Network, this is a snapshot of it is today, there are three primary sites: Madrid, Goldstone in the US, and Canberra in Australia. And because of this, they slightly overlap such that there is complete 360 coverage of anything that's way out there in the world. So this leads us now to the Voyager, and earlier was mentioned some of the challenges of the laws of physics. No matter what great software I might write, I'm not going to be able to transmit information faster than the speed of light. The Voyager is way out there. In fact, its one-way light time to Voyager 1 is about 21 hours. What's remarkable, and remember, this is a spacecraft that's decades old. It has about a 22, 23 watt transmitter, which means by the time that signal gets out back to us, Voyager 1's in interstellar space, it's about a billionth of a watt. And the Deep Space Network is able to receive that and interpret that data. Uplink speed from Earth to Voyager 1 is about 16 bits per second, and downlink is about 160 bits per second. So, really, really slow, as you might imagine. Today, there are somewhere on the order of 6,500 satellites in Earth orbit. Some are in LEO, many are in geosynchronous orbits, lots in between. If Elon Musk has his way, there will be many, many more thousands of them out there. Of the 6,500, about half of them are active and about half of them are not active, which of course creates a problem unto itself of potential space debris, but that's another problem we won't deal with. And the communications we're beginning to see from space to us, the satellites that allow us to look at our Earth and communicate with one another, the communication infrastructure here is absolutely amazing. It truly is. And it evolved out of basic need. Now, what we're seeing emerging is, again, this demand pull with more and more satellites in low Earth orbit, with us having really the next generation of commercial space travel. There are engineering needs to start putting more and more things in the cloud itself. And to that end, you'll see proposals such as this, and there are many others, for taking the cloud that is actually on the Earth, terrestrial cloud, and moving it into space itself. So what we're seeing is, because of the physics of data, the fact that there is a cost to transmit that data back to Earth, and the fact that I can do some of that computation at the edge, now at the edge of space, it makes sense to move the cloud out there. Indeed, Nokia has a contract with NASA and Bell Labs to actually put, I think it's 4G, not 5G yet, on the lunar surface. So there's a project taking place there. So we're beginning to see those communication networks begin to take hold. What's the protocol that's in place? If you look at all the deep space networks, what's remarkable is the resilience, really, of the networking standards laid some decades ago. And what we have working primarily over TCP/IP is a bundle protocol, which is basically a mechanism used for DTN, delay and disruptive tolerant networks. It uses a store and forward technique. So when we're talking to Perseverance on the surface of Mars, there are many times the time of light issue is about what, 17 minutes, I think, somewhere around there. And there are times, even because we have the presence of the deep space network, we simply can't communicate with it. And we also know you got to deal with cosmic storms and the like, nasty stuff. It's a pretty noisy place out there electrically in space. And so what will happen is that down on Earth, we'll transmit up packets. They'll get stored through the Mars relay system. There are two satellites going around Mars. One, the Mars Reconnaissance Observatory, and then there's a weather satellite, if you will, going around Mars, and those are used together to relay information to it. Again, showing you the amazing resilience of the engineering that takes place here. NASA today has a space communications and navigation division, and they're the ones who are putting together this infrastructure. So we see already a number of LEO things that allow us to connect to the International Space Station and the like. The ISS, by the way, is due to be commissioned sometime next decade, and so we're beginning to see proposals for next generation space platforms which are commercially driven, which will again leverage this kind of communication pattern. And they're looking beyond as we look toward going back to the moon. Again, the Nokia work helps us there. As we move from the moon back to onto Mars potentially, then we're reaching these networks further and further out. So indeed, as we move ourselves toward Mars, there's an interesting problem of communication because, well, it's the HAL problem. HAL from 2001: A Space Odyssey. Because of the time of light issues, you can't rely upon mission control on the ground. You have to take mission control with you in the skin of the Orion spacecraft, or if you're Elon Musk, in the skin of one of his spacecraft. And so we're beginning to see the edge move out in a very big way to spacecraft themselves and to the surface of other planets as they move apart. So what's the lesson here, and what's next? Well, I look at it this way from an engineering perspective, and I think another speaker alluded to this as well. Um, from an engineering point of view, we don't build perfect systems. We try to build systems that are reasonably optimally solving the problems at hand. And we try to give solutions that balance the forces upon us. The usual cost schedule, mission kind of things. Uh, I've got the forces of risk and ceremony. If I'm building something whose failure might mean, gee, I won't get this latest cat picture, not so much of an issue. On the other hand, if I'm building something that if it fails, global thermonuclear war happens, you're going to add a little bit more ceremony to it along the way. And then, of course, all your illities. These are the kinds of things that pragmatically draw us to build systems of any kind of system. If you look at it from a different perspective, on the left-hand side, this is our imagination. On the right-hand side, ultimately, I'm turning these things into raw, running, naked code. There are a number of things that keep us in between. Obviously, the laws of physics, as we've discussed, algorithms are another barrier. The Viterbi algorithm was, of course, an important one in cellular communications because theoretically we knew that there's signals in this noise, but Viterbi gave us a way through his algorithms to be able to extract that signal in a very good way. So we'll probably see these kinds of algorithms continue to develop. Many of the communication ones are frankly decades old. We're beginning to see interesting algorithms starting to take root in the quantum space, starting to see noises with regards to quantum deep space communications. So this will be an interesting one to watch. But for most of us, the problem is, how do I build systems out of these? And to look at it another way, and this was also alluded to in another presentation, what are the forces that are going to drive the next generation communication systems? Well, the earliest things we built, and we're talking now in the 40s and 50s, the problems were just fundamental. How do I write an algorithm? And as we move toward the age of symbolic computation, the IBM 360 and the like, the problem was one of managing complexity. And then as we moved to personal computers and mobile devices, it was HCI. We're mostly in the age of managing scale, but increasingly it's the rise of these imagined realities that bring to the table ethical and moral issues. Probably nowhere in the history of computing has it been true that ethical and moral issues are impacting the technology that we build, and they're certainly going to impact the technology that we have for any kind of future communication. So cool. This is the future. I'm terrible at predicting the future, so I'm not going to even try. But I will tell you, these are the forces that I see that are going to drive us there. And from the perspective of looking at this from space, there's a whole lot of really fun engineering going on that we're building to make this real. So thank you.
Thank you, Grady.